Daniel Selsam. I work at Microsoft Research, and I'll be presenting the IMO Grand Challenge. And I want to start by reading the third paragraph of the now standard deep learning textbook, and the underlines are mine. In the early days of artificial intelligence, the field rapidly tackled and solved problems that are intellectually difficult for human beings, but relatively straightforward for computers. Problems that can be described by a list of formal mathematical rules. The true challenge to artificial intelligence proved to be solving the tasks that are easy for people to perform, but hard for people to describe formally. Problems that we solve intuitively, that feel automatic, like recognizing spoken words or faces and images. Now, I think there is a basis for this claim, but the sad truth is that we're nowhere near human level, even on formally specified problems. Computers are really only superhuman in certain niches, so problems with simple algorithms such as differentiation or with limited structure that can be solved by SAT solvers, or in certain decidable first order theories that can be solved by conference closure or simplex. And there are many others here, but I think such feats have really masked the lack of progress on the general problem. It can still be hard to even produce machine checkable proofs at all, as many of you know, even for relatively obvious steps after building libraries of abstractions and tactics, even with real-time interaction and feedback after decades of tool building. And this is true in both mathematics and software verification. Now, arguably the norm in automated reasoning and in many scientific fields is to work forwards from existing methods. So come up with better heuristics for existing search spaces or more efficient data structures for existing algorithms, perhaps develop procedures for new theories that can slot modularly into SMT solvers. And this approach has obvious pros. You can often push technologies much further than expected. And again, this happens and we cross thresholds that unlock important applications. But in the long run, I think it can be a little too easy to ignore the ultimate brick walls of certain approaches. I claim that existing paradigms will never get us to human level reasoning. Now, in contrast, working backwards from a goal is not a panacea. So some goal arbitrarily out in the future, it's vague, it may be wholly unclear how to make any progress at all. It may be possible to measure progress, or really the worst, it may just require a lot of one-off engineering and not lead to any scientific advances. But the right goal at the right time can really be powerful. It can trigger the right questions, suggest promising new approaches, bring together siloed subfields, and at best it can lead to revolutionary advances. And my claim is that the IMO is the right goal at the right time for this community. So let's talk about the IMO. It stands for the International Mathematical Olympiad, as many of you know. It is perhaps the most celebrated intellectual competition in the world. It's held every year. More than 100 countries train and filter their 6 best high school age students. It's a 2-day test with 4.5 hours for 3 problems each day. So the problems take a lot of time for the humans. And the medals are percentile based. So roughly the top 8% win gold medals. All the material is elementary. So in principle, it's only high school level mathematics that is required. There are 4 subject areas: algebra, number theory, combinatorics, and geometry. And the solutions tend to be short and sweet, but they are designed to require tremendous ingenuity, even for people who have studied all previous problems and their solutions. And suffice it to say, it's extremely, extremely elite. I'll quickly go through a few example problems, just the statements to give a feel for the kinds of problems we're talking about. Here's one from algebra. Let x, y, and z be 3 positive reals whose product is greater than or equal to 1. Prove that this inequality holds. This happens to be in a decidable fragment, nonlinear real arithmetic, but the quintics make this very, very difficult for brute force methods. Here's one from number theory. Show that for each prime p, there exists a prime q such that n to the p minus p is not divisible by q for any positive integer n. Again, it's a very, very simple statement, only requires elementary math to state, easy to formalize, but presumably the proof requires some ingenious steps. Here's one from combinatorics. Again, very simple to state. Let p be an odd prime number. How many p element subsets A of the set from 1 to 2p are there? The sum of whose elements is divisible by p. Again, very easy to state and understand. And then here's one from geometry. I'll skip this, it's a little bit more complicated, but again, it's relatively easy to state and formalize. Now the challenge itself, the IMO Grand Challenge, is to build an AI that can win a gold medal in this competition. And we advocate the formal to formal, or we sometimes shorten to F variant of the IMO, where the AI receives formal statements of the problems in a formal logic, and must produce formal, i.e. machine checkable proofs. A few other details: the system must be checksummed before the problems are released. So there's no possible way that the programmers or any trained neural network system can have peeked at the test data. It gets no access to the internet. It gets the same wall clock time as humans, but there are no other computational limitations. So you can use arbitrary amounts of parallelism. The proofs must be checkable in, say, 10 minutes. It's somewhat arbitrary, but it's roughly what it takes to check a human proof. And we don't want solutions that are too brute force that would take a ton of time to check. And we have a committee including stakeholders from many different organizations. So Leonardo Demers, my colleague in Microsoft Research, Kevin Buzzard is at this conference from Imperial College London, and there are several other people from Stanford, Apple, a few other universities. So why the IMO? First, it's an extremely simple setting. Problems are formally specified, so there's no vagueness or ambiguity. Solutions can be machine checked, so there's no need to imitate humans. There's no need for qualitative assessments of progress. There's no Turing test like deception aspect. It's all unnecessary. And it's a closed world. There's limited background knowledge required. And yet, despite this, there's a broad consensus that this task is incredibly hard, maybe even foolishly hard, maybe even AI complete, that it would be among the all-time great achievements of computer science, and clearly the winning tech would revolutionize AI, automated reasoning, programming languages, and mathematics. And maybe most importantly, there's an ongoing supply of new problems. There's a long-standing, really fascinating global decentralized process to collect new problems each year that are in this closed world that can be solved with known methods, but that are still thought to be extremely difficult, even for people who've seen all previous problems. And there's a well-defined notion of success, which is another fantastic thing to have in a goal that you're striving for. And most importantly, I think we have a real chance at potentially actually winning this competition and getting a gold medal. But we need to work together as a community, I think, and we need to play the long game. So I want to talk about our high-level strategy, very high-level strategy for now. The first part, and really the driving force of the project, is to formalize historical problems in need. There was already a grassroots effort in the MathNet community even before we announced the IMO Grand Challenge, and many former winners, some of the best of all time, are involved, and most of the background math is already there. In fact, just the incredible, it's really an incredible social phenomenon in the MathNet community, and they're some of the smartest people I've ever gotten to work with, and their enthusiasm is a big part of my optimism about this. The second part of the strategy is to compress proofs using very high-level tactics or abstract strategies, the kinds of strategies that humans are taught that you might read in Polia's How to Solve It book, for example. So here are a couple that are taught in Olympiad problem-solving books. There's the small n strategy, which is to consider toy examples of the problem and look for patterns there. There's look for symmetries, consider the extremes of certain quantities, look for invariants, try to find some clever way of applying the pigeonhole principle. And there's a big challenge here, which is how do you manifest these pretty abstract, almost vague strategies in software? The third part of the strategy is to train neural networks to guide search. Now, these very high-level tactics will hopefully prune the search space from something a priori hopeless to something merely intractable. But they'll still be riddled with choice points. There's no way to hand engineer all the low-level heuristics. Even when you write these strategies, they've induced exponential search spaces. So the big challenge here is how to learn heuristics from a few examples. For any given strategy, there might only be a couple instances. And there are only a couple hundred IMO problems, only a couple thousand Olympiad problems. So clearly we need to, if we're going to use neural networks, we need to figure out a way to pool data across many different domains. And then, if necessary, we finish the job with an armada of search. Of course, it would be great if we can just solve these things in a few minutes on a laptop, but if we need to, we will throw a lot of search at it. So here's an outline for the rest of the talk. The standard advice for talks is to stick to the past, talk about what works, what's bulletproof, what you're sure about. Contra that advice, the rest of this talk is going to be a preliminary roadmap. It's informed by real experiments and real prototypes, but it is really very far from battle tested. So this is a caveat to the rest of the talk. The roadmap might look different in a year or two, but I think this is a very plausible starting point. And I'll be presenting two interrelated work in progress ideas. The first is representing strategies with something we call the search transformer. And the second is guiding search within those strategies using what we call the universal oracle. Now, I'll be presenting things that are at least slightly on the hand-wavy side of things, but the real war machine that makes these projects possible is, of course, Lean 4. It's a similar logic as battle-tested by Mathlib, but new in Lean 4, it's a real programming language with really ridiculous performance. So before, if you're trying to optimize tactics or gradually add more search to tactics, eventually you'd hit a point where you needed to drop down to C++ for the performance critical parts. And now in Lean 4, the functional language itself is so fast that there's a smooth continuum of gradually adding more and more search and more fancy data structures to the tactics. And it's being built by Leonardo de Mura, my colleague at Microsoft Research, and Sebastian Ulrich at KIT. Okay, so the standard agent environment model for ITP is perhaps you have a set of theorems in the environment, you have a current goal, you take an action in that goal, and you get a list of sub-goals back. This is the standard tactic framework abstraction, simplifying a few details. The outer loop is you look at the theorems and the current goal and the possible actions, you select an action, and you apply it. Maybe you generated the action with a generative model. You apply it, you get a bunch of new sub-goals, and you add the sub-goals to the goal stack. This is an appealing formulation, but it has pretty serious limitations. So it creates this artificial binary distinction between choices for which we want heuristics and black box tactics. But in much of formal math, the line is very blurred. Really, tactics are computer programs, not atomic actions. They may keep their own state, not necessarily just a list of goals. They may make their own internal heuristic decisions for which you would want guidance from a network if possible. They may call other tactics recursively, and indeed, compositionality is where their real power comes from. So the first part of our roadmap is a new agent environment model for applying neural networks or any kind of heuristic guidance to theorem proving. And the idea here is that we write non-deterministic tactics with explicit choice points. And the agent's job is effectively to execute these tactics, choosing which branches to go down at each choice point. Now, the status quo in tactic frameworks is that a regular tactic will hard code any choice point order. So if you use the or else combinator, F or else G, really this means try F, and if it fails, try G. But it's the program that tries F, and if it fails, try G. I can't easily write a meta program that runs this tactic using different heuristics. The search space and the search decisions are completely intertwined. So our approach, in contrast, is to reify the choice points, to factor out the heuristics from the search space and allow multiple modular ways of guiding tactics or strategies. Here's a silly example. There'll be more details later. You can imagine writing a non-deterministic tactic blind rewrite that first chooses a theorem from the environment and tries to rewrite with it. And then you can potentially write different generic search procedures like breadth first search or depth first search that take this non-deterministic tactic object and run it using different policies. And there's a big open question here, which is how best to encode IMO strategies. I'll point out two useless extremes for contrast. Useless extreme number one is you write detailed proof scripts, kind of like what would be currently done in a formal math library, where there's no search to reproduce the proofs. This is a useless extreme because that exact script is not going to work on a new problem. Useless extreme number two is your non-deterministic program just chooses the individual bits of the proof and then sees if it is a proof of the theorem they were looking for. This is useless because it's totally insane search. There's no structure, there's no guidance, there's no reason to think that heuristics can help you navigate it. So obviously we want something in the middle, but the exact where to draw the line is unclear and really depends on how much we can rely on our heuristics. So let's look at a few examples. Here's some Olympiad inequalities. Here's an example. Let A, B, and C be greater than 0 and prove that this thing holds. Some of you former Olympiad winners might have already spotted that this is an obfuscated instance of Holder's inequality. And here's the human calculational proof. The details don't matter much. First you group things, you cycle something. Now you can apply Holder's inequality. You apply Holder's and then you just cancel things and reduce and the theorem follows. But the high level proof is that you make the left-hand side look like the left-hand side of Holder's, you apply it, and then you're done. So it's easy to implement a non-deterministic strategy that can prove it by encoding that high-level proof. And this is an example. First, you choose a theorem non-deterministically from the standard dozen, which is the name for the 12 theorems you're allowed to cite without proof on Olympiad inequality problems. Then you have this subroutine make look like that specifically tries to make the left-hand side of the goal look like the left-hand side of that theorem using, it might do search internally, but it knows it's goal-directed search. And there might even be procedures for certain special cases. Then you apply the theorem and then you finish. Finish is like simplify, just do easy things. And now it might be really, really hard to specify which theorem to try next. Maybe you can think of 1,000 lines of special heuristic rules and if statements and gates and guards, but it's really a nightmare. And it's really, it might be hard to even write make look like, even though it might be deterministic. It might be a very complicated algorithm to write out explicitly. But the simple script above is already extremely, extremely useful. In particular, make look like gets a specification that it can use. So it's not blindly searching. It's goal-directed searching as a subproblem. It can use that target to prune the search space dramatically. And it's also easy to relax the proof much further. So you can replace getting the left-hand side of the goal with choosing from the subterms in the goal. You can change apply to rewrite and finish to simplify and recurse. And now this script is a pretty not unreasonable encoding of many, many inequalities problems and solutions. You need a couple extra tricks. You need homogenization and a few other things, but this abstract skeleton already covers quite a bit of the toolkit for Olympiad inequalities. Let's look at geometry now. So here's a geometry problem. I won't go into the details of how this is constructed, but basically you're trying to show that DE and FG are parallel. And now most geometry proofs require introducing auxiliary constructions. So for example, midpoints, feet, intersections of lines and circles, circles and circles, reflections of points around points and points around lines, completing parallelograms, etc. And there's a large, indeed infinite set of possible auxiliary constructions. And these constructions are sort of celebrated as the moments of human insight and ingenuity. The human proof of this theorem starts, let M and N be the arc midpoints of A, B, and AC respectively. It suffices to show that FG is parallel MN and DE is parallel MN. But what magic? How do you know to try M and N? What is the abstract strategy here? And the answer is to look at the diagram. So if you look at the diagram, you see that M and N, these points happen to be parallel to the two things you're trying to prove. So really, what's happening is that you're applying the transitivity rule for the parallel relation, and then you're looking at the diagram for points that you can add that would satisfy that property. So here's the simple non-deterministic strategy that includes that action. First, non-deterministically choose one of your geometry theorems, apply it, and if there are now metavariables in the goal, look at the diagram to find points to instantiate those metavariables with, and then recurse. And again, you have no idea how to specify which theorem to try next. It's a rabbit hole trying to write down those heuristics by hand. There might be many options in the diagram for points you could add that have this property. So you've really no idea how to write which of the promising constructions to try next. But as for the inequalities, the simple script is already extremely useful. So the candidate constructions are proved by several orders of magnitude, and there's no loss of power as long as the model is correct. In geometry, the models can be very precise. But the best tactics, I've been stressing this all along, the best tactics will still induce intractable search spaces. We can only introspect so much. We can only provide so much structure before we dull the system. So obvious question is, can we leverage learning to navigate these spaces? And I hypothesize that learning has so far failed to advance automated reasoning for three related reasons. So search spaces being too low level, wrong agent models, I've discussed those already. The obvious elephant in the room is not enough data. I think everybody agrees on that. So the second part of our roadmap is extreme genericity. And the idea is that we're going to embed search problems generically so that a single neural network can pool data across all conceivable search problems and provide zero-shot guidance for a new search problem. And of course, be fine-tunable. So we want to pool train data across many domains. So obviously IMO problems, mathlib proper, of course, other formal math libraries such as MetaMath, maybe computer algebra. It's easy to generate reasonably interesting synthetic data for integrals and sums. Synthesis problems such as the abstraction and reasoning competition, or maybe things that arise in flash fill or things like that. There's also a bunch of synthesis benchmarks out there. There are all sorts of puzzles like Sudoku. We could also do verification problems, maybe code optimizers, query planners, board games. It's endless possibilities. It's really just an empirical and an economic question where to draw the line. But to pool, the search problems must be made commensurable, and that's one of the main conceptual barriers to doing this pooling. So we introduced a new abstraction called search T for representing arbitrary search problems. And I've made a point to not have any abstract nonsense or incomprehensible pseudocode. So it's all going to be English language descriptions, but for the functional programming aficionados, search T is just a monad transformer that adds non-determinism to some base monad. And that's all I'll say about that. The basic idea is a search problem is an arbitrary program that either fails, successfully returns a value, or returns what we call a choice point, where a choice point is some user-specified data deemed relevant for the decision. You can go to some snapshot of the program state and a list of possible choices, where each choice is some data summarizing the choice, which you can think of as features, but it could be an arbitrarily structured object, and another arbitrary search problem, i.e. just a continuation of the original search problem. And you can run a search T program in a variety of generic ways. You can write depth first search, breadth first search. All the examples I showed you before are really, the non-deterministic tactic monad is really just search T. And we'll talk very soon about how to write generic heuristic search. And I want to talk about one example that has nothing to do with the IMO to show how general these abstractions can be. So this is a problem from the abstraction and reasoning competition. It's a fantastically interesting data set, synthesis problems created by Francois Cholet at Google. And the idea is the agent sees just a very small number of input-output pairs. So the top row are the training inputs, the bottom row are the corresponding training outputs. And then you get a test input and you need to output the entire test output. So in this case, you just find the shape that touches the gray and you take that shape. So the output is just this, it's pretty simple. The high-level solution here is you split the input into shapes by color and connectivity. You find the special shape, in this case, the one that touches the gray cell, and then you guess the smallest square containing the special shape. Now, here is another problem which is much more devious looking, but it's actually abstractly the exact same strategy. So you split the input into subgrids by stripping the partitions. Okay, so in the upper left, you get these 9 different 3x3 subgrids. You find the special subgrid, in this case, the one that has only 4 cells in it that are non-blank, and then you guess some transformed version of that special subgrid. In this case, you upscale it, and then you add the gray separators back. And I did the bold to stress that it's really the same recipe for both. And here's a search T program that can actually solve both. So first, you non-deterministically split the input into things, and internally, non-deterministically, that will try parsing into shapes where colors mean different shapes, where colors mean same shapes. It'll try partitioning in various ways into subgrids. It tries all sorts of things, but it's compositional, so the details are abstracted here. And then you're going to just try to look for some special thing that you can align in some way with the output. And it gives you back a special input for each example and this into-out transformation function. Then you're going to call basically a generic program synthesizer and synth pick special function here, which gets the special input and the in things. And it's just trying to learn a program that can predict the special input given the set of all of the in things. And then your guess is just on the test, you parse the test, you split the test input, you pick the special thing, and then you apply the output transformation. This is a little hard to follow, I'm sure. But it's just codifying this high-level solution that we wrote before. And the point is that it works very well, and it works compositionally. So a handful of search T tactics like this placed us in the top 2% of the Kaggle art competition. And we didn't have any heuristics. We only had blind iterative deepening. This is all joint work with Ryan Kruger from University of Michigan and Jesse Michael-Hand from UPenn. And I'll just quickly take a tangent to say that Jesse is at the conference. Many of you already know him. He was my intern just now, but before that he did an internship with John Harrison at Amazon. And they have some very cool results using neural networks to speed up real stat solvers. And he'll be presenting that on Thursday. You guys should go check it out. And he has many insights into all of the things discussed in his talks. He was part of most of these experiments. So definitely talk to him. The takeaway from this ARC example is that programs plus non-determinism let you write convenient, abstract, compositional strategies that can solve problems that superficially are completely unrelated, but that are unified at a very, very abstract strategy level. And note, we need to be conservative in our ARC solver to keep the search tractable because we had no heuristics. So we had to play the gating game or the guard game to make sure that tactics don't try too many things that we think are unpromising. But we could have written much more flexible tactics if we had a source of heuristics. So this brings us to the heuristic problem. So recall a choice point consists of some user-specified data deemed relevant for the decision, like some kind of snapshot of the program state, and a list of possible choices, each with summary data, like the features, and a continuation. But the data, so it sounds easy to embed, but the problem is that the data types involved may be arbitrary. So in the inequalities example, maybe it's just a regular tactic state that you have, but in geometry, you might want to represent the geometric scene using an E-graph or possibly even special data structures such as sets to represent line and circle membership. The diagram is these numerical coordinates, which is not easily crammable into a regular tactic state. And in ARC, you want to store these input and output grids, and you want them to be grids, not just ASCII. In all three examples, the subproblems see different data as well. So in inequalities, make look like sees the target pattern. In the geometry, choose from model sees the property you're trying to synthesize. In our example, it was 2 points that are parallel to D and E. In ARC, the synthesizers that you call a subroutine see labels. In fact, they don't even see the original grid. They just see this data set that your tactic created for it. So the question is, how do you share statistical strength across all of these diverse problems? And the first thought is just to emit tokens and use a single transformer. And this is appealingly simple, but it's really naive. It introduces terrible asymptotics and has very limited inductive bias. So the proposal here is that we use compositional embeddings. So for example, we might embed list of alpha as, say, an LSTM on embeddings of alpha, where the embeddings of alpha might be recursive. A vector of alpha as some kind of transformer on alpha, perhaps. Set of alphas as some kind of AC invariant representation of alphas, for example, deep sets. Grid of alpha as a CNN, which you might want to use for ARC or chess. You can embed some custom term type, either as, if you have enough specialized data, as your own new GNN, otherwise as some kind of parameterized, globally shared GNN. And again, you share the vector parameters across all vectors, the set parameters across all sets, so that you learn generic embeddings that are compositional. And now call this phase one of the embedding. Now, you also need to embed the continuations themselves as the program expressions. You don't need to do this in a tactic framework because the program is, the continuation is the same for every choice. It's just the outer loop again. But in an arbitrary program, it really matters what the continuations do. So you really need to embed them somehow. And you don't want to run them because they're non-deterministic. So it's arbitrarily expensive to run or simulate them. So the idea here is that we just embed the program expressions as a little bit of a glimpse into the future. And this would be the network's responsibility to summarize that usefully. And then phase two, after embedding all the data types to the same space, we can now run a single generic model that's shared across all of these input formats, such as the transformer. And of course, you can also pull data from Wikipedia and everything, because you have this core module that is being applied to any kind of task. And then at the end, you just output floats giving scores to choices. Now, using these ideas, we can embed arbitrary types into one space. Now, I won't talk about this, but there are language features, particularly type classes, that will make most of this plumbing transparent. That can just automatically synthesize the embeddings compositionally for your data types. And together, all of this lets us build what we call the universal oracle, which is a trainable procedure that can map any choice point with n choices encountered by any search T program into a vector of n floats representing heuristic preferences among the choices. And finally, we can implement self-improving universal search, which is a generic way of executing a search T program that queries the universal oracle at every choice point and also trains the oracle based on new data arising from the search. Because whenever you find a solution to something, you have good data points. Not just one, you have data points at the very least for everything along the trace leading to that proof. And that is the end of the roadmap section. And I want to quickly wrap up by speculating a bit about the significance of the IMO. my hypothesis, some of the committee members share this, but I can't speak for everyone. If we can win the IMO, we could use a similar methodology to automate any class of problems that A, are formally specified, and B, that very smart humans can be trained to solve reliably. So crucially, this does not include personal assistance, for which there's no formal spec, for which you just can't explain to the computer what you want it to do. And it also crucially does not involve solving clay millennium problems, because it's not a teachable method. You can't just teach people to solve clay millennium problems. But it is still a huge class of important problems. So it includes most proofs in computer science and statistics research, anything with convergent rates, regret generalization bounds, asymptotic time-space arguments. They're all, it's just over and over again, you've just got this bag of tricks, these strategies that are hard for humans to learn, but once they learn them, let them prove this class of problems pretty reliably. And it includes many subproblems that appear in real or proper mathematics. So actually many IMO problems arise this way. So we know that it includes these. And it includes a big chunk of software verification as well. Now, my personal long-term aspiration for this research agenda is high-performance synthesis from extremely high-level code. Now, there's a universal finding that it can be very difficult to write good declarative specifications. So it's a huge amount of work to develop a semantics for a serious compiler. I don't even know what a declarative specification would be for an operating system, but it's always easier, vastly easier to write slow code than fast code. So here is a mostly well-defined and mostly teachable to smart people problem that could have a large impact. You start with extremely high-level naive code, and the system performs all sorts of high, medium, and low-level optimizations and ends with correct super high-performance code, plus some additional desiderata, there might be cost models and so forth. And I think that if we can win the IMO, perhaps we can automate a big chunk of this process as well. And thank you very much. That's all I have today. I want to thank many people. A lot of this was joint work with Jesse Michael Hann and Ryan Kruger. Almost all of this has been done in collaboration with Leonardo Demura. The MathLib community was extremely helpful in framing the IMO Grand Challenge, figuring out the rules, figuring out whether it was feasible to encode and formalize. So I'd like to thank them as well. And that's all I have. Thank you very much for coming.
All right, thank you very much. And it's time for questions. There's nothing on the chat yet. So, anybody in the room? Go ahead.
All right, so one question, just kind of simple question about the presentation. Like you were showing some of the IMO problems, so I'm interested whether you first tried to solve them by yourself or you read the official solution for it.
Read the solutions. Basically, we took a similar approach as we did to the ARC solver. Let me go back to this. We basically we would take a problem, look at the solution, and write some very abstract strategy for it, look at the next one, and then refactor, add modules to the strategy or relax the strategy so that it covered both problems. So that's the outer loop. You look at the n plus first problem and you see if you can already solve it in a reasonable way. Not necessarily quickly, but that it's in your search space, that you have the important abstractions there for there to be a short proof. And if there is not, hopefully you just modularly add to some component, like maybe you just add a lemma, and modules that can use lemmas now can be more effective, or possibly you need to add something qualitatively different to one of the strategy scripts. But the idea is that you're maintaining a small set of non-deterministic strategies that you're gradually relaxing to cover more and more of the space.
I have a second question.
Yeah, go ahead.
All right, so second question is something that I was already talking, discussing a bit on Zulip. And it's like, I like this idea of non-deterministic strategies for sure, but it still requires the right input for the agent.
Sorry,
And
I'm having trouble hearing. It still requires what for the agent?
uh, well, the right input, right? So you were talking about the input, how you encode the input for the agent, right? But like sometimes the agent is not just like deciding by the input, but by some other, let's say, exploration strategies. That's what I think people do the first with IMO problem, that they just try something, look at how it behaves on small numbers and things like that, even though they don't have to have any specific strategy how to solve it in mind yet.
But that kind of strategy can be written in this framework. You first small n, you collect hypotheses in a data structure, and then you call another non-deterministic tactic that has that new state
You
with the
collect
results.
intuition. I'm not sure whether you really collect, but okay, like, okay.
Well, so the current framework as I've presented it is assuming that strategies like that would be written within search key. I think you're asked, there's another way to interpret your question, which is instead of only seeing the current choice point with the snapshot there, might you have generic heuristics that also see, for example, the state of MCTS and get to actually have neural embeddings of different leaves to transmit information during the course of a single search across the search tree. I think that's an interesting direction. My hope is that it's not necessary, that we can write the search tree problems in such a way that we build in the kind of communication that we want, but it might be possible to train generic heuristic procedures on top of this that do get to look at the search data structures themselves, as opposed to just the non-deterministic program state.
Okay.
Right. I see a number of raised hands in the list of participants, so I will ask the first one to ask you under the nicknames.
Thank you. First of all, great and very motivating talk. Thank you very much.
Wait, sorry, who's talking? I'm having trouble scrolling.
Stanislas, here. I'm on the
Still
video.
looking for you.
Do you see me?
I see you now. Hey.
Okay, cool. So great and motivating talks. Thank you very much. My question is, IMO seems to be very out of reach for any system that we have out there. Is there some motivation to maybe to get the ball rolling and get the community together to kind of challenge ourselves and get us to make progress as a community? Any appetence or willingness to create kind of maybe a IMO middle challenge or
Sure.
IMO?
I think geometry is qualitatively easier than the other three domains. So just having like a restricted challenge for getting the geometry problems for a given year, I think is really very much approachable. We already have a prototype solver that can solve a bunch that we didn't.
And is there a way that we could, let's say, we've selected these problems for, let's say, 2020 pre-partial IMO Grand Challenge, which is not at all IMO levels, but we decide that these problems are what we want to tackle, and we kind of formalize the statements in many language, and we all can chew that together.
I'm very reluctant for test sets that are known by programmers. I really think it's important that you have to checksum your solver and your network before you or your network get to see the problems. But there are Olympiad problems at many levels that are released each year. So we could aggregate. So geometry problems are solvable. It's definitely not some pie in the sky thing to solve them. And we could pool test problems across the short list and other sources of Olympiad problems to get a reasonable evaluation set each year. So that's one idea. I'm very open to if you have other suggestions.
Well, my main point was like just to get things started, even if we know that nothing is perfect, the systems are not perfect, the formalization efforts are not perfect, the problems are too hard. Let's try to kind of get the minimal sets such that we can start, let's say, this year to challenge ourselves on something as a community.
I'll think more about it, but I think geometry is a very, very reasonable starting point. Certainly by next IMO, it should be something that many different groups could do.
Cool, thanks.
Right, thank you. The next is Kevin Bazel, so asking to unmute and ask the question.
Can you give me a second to find him in the sliding list? Hey,
Hi. So at the very beginning, you stated a combinatorics problem, and that problem is somehow unformalizable, and you didn't even mention this.
I didn't. Oh, wow. What is it? Oversight. Let me go back to it.
Well, I didn't hear you mention it anyway. It was like the second slide or something.
I think it's just an oversight.
Oh, here we are. Yeah, what does that question even mean? I mean, it's just some function of P.
Yeah. Oh, that is the determinant issue. Yeah. So I glossed over this in the talk, or actually didn't mention it at all. But there was quite a bit of discussion on Zulip about this. There are some problems that are not really formal statements that require synthesizing some kind of a witness, and there might be cheap or unfair ways of representing that witness that the logic itself cannot distinguish between an answer that we would accept as intelligent versus a bogus answer. For example, you could return here just some object saving the size of this set without giving any details. Yeah, so I didn't go into this in the talk, but the plan is to actually have one part that might be judged by humans. So for all of these witnesses, the humans will look at the witness and confirm that it is reasonable. But then all of the proofs given the witness will be automatic. So the idea is that the witnesses are simple and short enough that it's not a burden. And it shouldn't be
That's
too
implicit in the question. I mean, I know exactly what the question is asking. It's asking you to find a cute formula for it, right? That's
yeah.
But it doesn't explicitly say that.
And there's lots of games you can play. You can write some totally intractable procedure that computes to a formula for it, but in exponential time. And we want to not allow that. And yes, we require humans in the loop for that part. Mm-hmm. Good question.
Right, thank you. Bob is the next. I'll ask to unmute.
Hey Dan, great talk. You won't find me. I don't have video.
Is this live?
So it seems like the crucial part of your roadmap is in having a search T high-level program for every problem you'll encounter.
Ideally, it ends up as one program that is solve IMO that might make choices for whether to try geo or, it doesn't need to be non-deterministic choices. It can look at the goal and make a deterministic choice. But it ends up being one thing that you call that is the solver. And it might consist of dozens or worst case hundreds of different strategies composing in various ways, but with one entry point. I'm not sure if that was your question. Do you mind rephrasing?
So, so that there's some amount of human work in writing the search T program.
Yes.
And like you said, there might be hundreds of different sub-programs that might be called, and that basically you have to humans have to go through all of the IMO problems and add new subroutines and so on until the whole space is covered.
But yes, it's not really clear yet how quickly that fixed points. Inequalities, you get very far with the relaxed version of the one above and a few other programs. So it's an empirical question in domain by domain, just how easy it is to write adequate strategies. I think a really important part is that I agree with the negative conclusions from what's broadly classified as good old-fashioned AI, that humans simply cannot write the heuristics for when to do these things. But at the level of abstraction at which I'm advocating we write these strategies is very easy to elicit. So I think it would be not the right path if every new problem we need to write tons of specialized code. The hypothesis here is that there will be a lot of compositionality and a lot of sharing across the problems, and that it will reach a fixed point in a reasonable, after seeing a reasonable number of historical problems.
Is there any hope of sort of relaxing this templated structure at some point and just letting the network do the low level and the high level decisions?
Sure, you could probably even automatically have a relaxer that removes structure from search spaces and still try to train the network to make those bigger jumps.
It seems like you could even just train a language model to produce, I mean, these are short programs.
Yeah, I mean, you can do all of that stuff, but in terms of plausibility, I don't think there's a world where a 200 layer transformer is going to spit out the proof to an IMO problem from scratch. So maybe that's a hypothesis that other people in this room have, and that's fantastic. I personally think that there'll need to be quite a bit of this human provided structure. And I do hope that we can relax it and that it can be as minimal as possible.
Okay,
Possibly even more and more minimal over time as the universal oracle is trained and gets better and better.
Thanks.
Okay, Stefan Schulz is the next.
Hi. Yeah.
Yeah, go ahead.
Hi.
I've got one remark and then maybe half a question. I was very surprised to learn that machine learning has not helped improve automated reasoning, which you had on one of your early slides.
Maybe too oversimplified statement. I think it hasn't been revolutionary.
I think at deep learning has been disappointing. Yes, but there's a lot of other more symbolic work that works well. You can maybe talk to Joseph, who probably hit you over the head with a
I absolutely agree. I meant that to mean the kinds of big networks that I was proposing to use for this problem. I didn't mean to include anything involving all things that involve statistics or numbers or differentiation.
And I have to say, I really liked the talk, and I think this is a fantastically interesting project, but it may be one of those where progress comes a small piece at a time, where you really need to have a few hundred students who build solver after solver after solver after solver before you can identify abstractable pieces, maybe get a more general approach.
Maybe there's a lot of this roadmap that, as I said, is not battle tested. I think there's a few forces where incremental progress is possible and measurable. So formalizing historical problems, that's a number that goes up. Writing, basically reducing the number of lines in the cumulative proof scripts that prove them is a number that goes down that we can measure. I see it as pretty decomposable and pretty incremental. You're gradually factoring out parts of historical problems. So I think the fact that we can point to some of these numbers and chart them over time is one of the things that gives me more confidence that it's not just thrashing blindly. But I think it's definitely a possible failure mode. I appreciate the warning.
Okay. Yeah, thank you. Next one.
Thank you.
Right, the last raised hand is Angela Gabi, so if you can unmute.
Hi.
Wait, I'm still scrolling through.
Sure.
Hi.
So my research group has also been measuring ourselves intelligent against the ARC data set. So I have a particular interest in how you did that. You mentioned that you would go through the data set, look at one task, look at another task, and then if possible, generalize the solutions for each of them. Did I understand that correctly?
Yeah. In fact, I have some cool, maybe this also addresses one of Vlad's questions about fixed point. So we did this first without looking at the evaluation set. So we just picked the training set, what problems for which we thought we knew how to write the abstractions that were necessary. And we wrote these abstract strategies that they look like this is almost exactly the code, but there's a lot of code inside the modules. So the parsing there's a lot of code, there's a lot of different ways of parsing. There's a lot of special cases in the partitioning that we wrote, but it's all very, very modular. So we did this for the training set, and in not that long, I forget the numbers, but maybe 60 or 70% we would get with just brute force search in a couple of minutes or so. And then we evaluated on the evaluation set and only got 20%. But the nice thing is that in just 2 days, without writing any additional strategy, just by adding new modules that slot in to the components, like adding new features, like whether a shape is symmetric or how many holes a shape has, we bumped that number from 20 to closer to 40 in just 2 days. So basically the abstract skeletons basically fixed pointed, and it was just a very modular task remaining to make the system more robust.
So this is something I'm wondering about in this program you show on this slide. This was presumably, was this program synthesized automatically?
No, we wrote this, but when
okay.
running it, it separately can prove this problem and prove this problem with
Okay.
very similar code paths. Like here, the splitting the input into things, in this case, the things are sparse shapes. And in this thing, the things are subgrids, but we're reusing the same skeleton for both. In this case, the transformation is just taking the enclosing square. In this case, the transformation is upscaling by 3 and throwing in these partitions. But again, it's all modular. So it's the exact same high-level strategy worked for both. But there is different code at the leaves for parsing into different kinds of things, for synthesizing different kinds of transformation functions.
And so when you decided on these modules you're showing here, like split input into things and choose special thing, those were ones that you guys as the developers decided would be useful,
yes,
correct?
Yes, that was our contribution.
Okay.
And
great.
basically, we just wrote out these high-level solutions in this kind of English pseudocode, and just looked for, thought, okay, what's the simplest strategy that'll get us the most new ones?
Great, thank you.
Great question, thank you.
There was a short question on the chat from Solrum Einar's. Maybe she wants to ask the question. Or should I read it?
I didn't hear that. Was there a question?
So the question from the chat says if you can attempt to find partial solutions to get partial credit on for the solutions.
It's still up for committee debate, and we're open to feedback. I think if the official solutions make it, if there's like an official consensus among the judges that if you got to this step, you got 2 points, then it's really unambiguous. We'll take it because it makes the problem a little easier. But in general, there's no wishy-washy. Only if there's like a real grading rule that you get this point for this step. Otherwise, no partial credit. But the details are still to be determined.
Right. Any question from the audience here? Okay, very good. So let's move to the next talk. It's about start.
Sorry,
Thank you very much.
yeah.